Okay, this is the first of 3 videos for Chapter 7. So they will be shorter videos, but 3 videos involved in this chapter before you do your review. This first video is on the planet Jupiter. And before we get there, let's compare the Jovian planets again to the size of the Earth. Here's the relative sizes of the 4 Jovian planets in relation to the Earth itself. All 4 are larger than the Earth, and all 4 of them spin faster than the Earth. Jupiter and Saturn on the order of 10 hours to spin once on their axis, and Uranus and Neptune on the order of 16 or 17 hours. Uranus is about 4 Earths in diameter, so is Neptune. Saturn is almost 10 Earths in diameter, so its radius is about 5. And Jupiter is about 11 Earths in diameter, so radius is about 5.5. If we compare the tilts of the Jovian planets, we know that Earth has a 23.5 degree tilt, and Mars is pretty close with a 24 degree tilt. Saturn is also pretty close with a 27 degree tilt, and Neptune a 29 degree tilt. So in terms of these 4 planets, their tilts are about the same range. Very similar. If we look at the planet Uranus, it's tilted on its side by 98 degrees. But if we look at Mercury and Venus and Jupiter, they're all straight up and down tilts. So Uranus being different from the other 3, these 3 having straight up and down, no axis tilt at all. We've had several Jovian space probes, in particular Pioneer 10 and 11 and the Voyager spacecraft, 1 and 2. Pioneer 10 and 11 had this plaque, partly designed by Carl Sagan, the famous astronomer. And the plaque was supposed to depict our race. We have the human male and female, and their relative size to the spacecraft itself, so that if an alien intelligence were to obtain the spacecraft, they'd be able to see what we looked like and what our relative size was compared to the spacecraft, so they'd know whether we are formidable or not. No, it's just so they'd get to know us. Then, based on the hyperfine transition of neutral hydrogen, the definite frequency of a characteristic element in the universe, one could use that binary system to figure out the particular distances to 14 pulsars in the galaxy. And if you triangulate these 14 pulsars, then you would be able to find our position in the galaxy. So at least that's what was thought. So even though this would be hard for any smart scientists on Earth to figure out, the idea is that if you were an intelligent race, you'd be able to figure out, triangulate our position in the galaxy, find our solar system, identify what was then the 9 planets. Of course, this would be confusing to a alien race that there was a planet called Pluto, because it probably wouldn't register as a planet in their mind, and then discern exactly where we were. The Pioneers 10 and 11 measured Jupiter's magnetic field as far out as Saturn, and they had this plaque depicting our place in the solar system. All these spacecraft that are going to the outer solar system, either to Jupiter, Saturn, or beyond, Uranus, Neptune, have to steal energy from other planets in order to get enough speed to get out there in a reasonable amount of time. So what they do is they employ what is called gravitational slingshotting. By using the gravitational field of the inner planet, the orbiter will come in and kind of pick up the speed with that planet and then kind of sling off, and hence grab free energy from a moving planet that's already moving pretty fast around the sun, and use that energy to help propel it to the outer solar system. So there's no way we could obtain that energy just through a rocket to get to these places in a relatively short amount of time. So sometimes NASA will shoot towards Venus first, like gravitational slingshot off Venus, maybe come back to Earth, slingshot off Earth before it goes off to, say, Jupiter. And that, in fact, that's what the Voyager spacecraft did. The Voyagers were slingshot off a interior planet, and they finally headed towards the Jovian planets. The Voyagers went past Jupiter, slingshot past them on their way to Saturn, and then slingshot past Saturn. Voyager 1 going perpendicular to the solar system, Voyager 2 continuing on to see the other two Jovian planets, Uranus and Neptune. So Voyager 1 observed Jupiter and Saturn, then left perpendicular to the ecliptic plane, and Voyager 2 was the only spacecraft to have visited all 4 Jovian planets, but not Pluto, and Pluto not being a planet anyway, but it did not go to see Pluto and continued outward in our ecliptic plane. Here's a gold record that was left with the Voyager spacecraft, again with the same symbol of the hyperfine splitting of the hydrogen atom to obtain the characteristic frequency of that pair, to use that frequency to calculate in a binary code the distances to 14 pulsars within our galaxy, and hence locate our position in the universe. This gold record also contained in a coded message greetings in 55 languages and 120 pictures, digital pictures of our life. Here's some other Jovian space probes. In recent years, we have gone back to Jupiter and Saturn through the Galileo and Cassini spacecraft. Galileo, launched in 1989, maintained Jupiter orbit for quite a while. It launched a probe into Jupiter's atmosphere in 1995, and as a result of that probe, found less water and lightning than expected in the atmosphere of Jupiter. In 2003, the Galileo probe was purposely allowed to fall into Jupiter and destroy itself, because it was believed then that we did not want it to contaminate Jupiter's moon Europa, which is of future interest for the possibility of looking for life. So we didn't want anything that might contaminate that moon before we got there with a more pristine probe. Cassini, launched in 1997, was headed towards Saturn and finally made orbit in the 2004-2005 time frame. And Titan, being the largest moon of Saturn and being having some characteristics of a primordial Earth, Cassini dropped a probe, the Huygens probe, into the atmosphere of Titan, which landed on Titan in 2005 and got some pictures and was able to make some measurements as it fell into the atmosphere. More on that probe later. Here's a look at the solar system, and we can see, all the inner planets within 1.5 astronomical units. You have the asteroid belt kind of separating the inner from the outer solar system, and then Jupiter 5.2 astronomical units away, so more than 3 times the distance from the Sun than Mars. Revolves the Sun around the Sun in 11.9 Earth years. Hence, every year you would see, say, Jupiter in 1 month. Say if Jupiter were prominent in the month of June, for instance, the next year it would be prominent in the month of July, because Jupiter would move 1 more month as far as Earth is concerned, because it would move the equivalent of 1/12 of its orbit in 1 Earth year. So every year Jupiter will be prominent in the next successive month of the year. It also undergoes differential rotation, which means that its equator rotates at a different speed than its poles, and in fact its equator rotates faster than the higher latitudes. So the equator is going faster than the poles, and that's an artifact of it being more of a gaseous planet. Here's some data on Jupiter and its 4 prominent so-called Galilean moons, because Galileo was the one to discover these 4 moons. So 4 nice pictures of Io, Europa, Callisto, and Ganymede. Here's a picture of Jupiter and one of those moons. It is the largest, so large, and it's also going to have a full reflection, being an outer planet, a full reflection towards Earth, and hence at its brightest, that 1 month a year, it will be brighter than any other star and brighter than most of the planets except for Venus. Look at Jupiter. 11 Earth radii, 11.2 times the Earth's radius, and hence 11.2 times the Earth's diameter if you go the full diameter. Its mass is 1,318 times the mass of the Earth, but its density is much lower than the terrestrial planets because its volume is so much larger. About 1,000 Earths could fit inside the volume, more than 1,000 Earths actually, fit inside the volume of Jupiter. Jupiter has a gaseous fluid composition. It's a result of strong gravity, so it has retained those gases and held them in, and low temperature, because the temperature is so low that the gas molecules can't get enough energy to escape that larger gravity. So with the higher gravity, low temperatures, it has retained even the lightest elements of gas. Completes 1 rotation in less than 10 hours. And the equator, as we said, is differential, rotates faster than the higher latitudes. Here's a look at Jupiter from the Earth, and you can see these 4 bright dots, which are Galilean moons. Galileo observed these 4 moons in 1610 through the early invention of the telescope. Jupiter has 62 known moons. And you can see most of them, even these are the largest ones, but they are much smaller than the planet itself. If you were to observe these moons on a day-by-day basis, you would see their positions change daily. The closest one, Io, goes around in just about 1.5 days. So you would see these moons change their positions daily, and you would basically observe, as Galileo did, that these moons were going around the planet. Here's the appearance of Jupiter. It's noticeably oblate at the center, which means that it's not purely spherical, but it's kind of egg-like shaped, with a oblateness or a greater diameter at the equator due to the centrifugal force of spinning. Here's Jupiter with 2 of its moons kind of superimposed on this picture. This would be Europa and Io. Io being a very reddish moon, Europa being an icy moon, and kind of neat in this picture. Jupiter is very distinctive with alternating light and dark bands across parallel to its equator. The white bands are composed mainly of ammonia ice crystals. The brown bands, ammonia hydrosulfide. So different chemistries going on in this atmosphere of Jupiter. Here's two moons again. This is probably Europa, and this is probably Ganymede up here. The black dots you see are probably shadows of these moons on the surface of Jupiter. The cloud bands that we see that give these bands of color on Jupiter are produced by convection currents and by Jupiter's rapid rotation, giving it sort of a jet stream effect in the outer zones of Jupiter, traveling much faster than the Earth's jet streams on the order of 1,000 miles per hour. Here's a great red spot that has been known ever since astronomers have been looking at Jupiter for more than 300 years. It's probably existed for thousands of years. There's no telling how long it's been around, but at least it's been around as long as astronomers have had the ability to see it. The red spot is the equivalent of 2 diameters of Earth across, so 2 Earths could fit inside the great red spot of Jupiter, this cyclonic storm. It's about 16,000 miles in diameter, and it takes about 6 Earth days for the gas to rotate once around this huge storm. Jupiter has other storms. It has this brown oval that's been around, and white ovals, other smaller storms, also discovered by the Voyager spacecraft. Longevity of the storms is due to the lack of landmass on Earth. If you had a storm and it hit a landmass, it would quickly start losing its energy. It would have no way to continue to obtain energy. But because of the lack of landmass on Jupiter, and mostly gaseous effects, these storms continue to go on and on and on. Closer look at the brown oval storm. Jupiter's cloud layer is 80 kilometers thick, composed mostly of hydrogen, 86%, helium, about 14%, and traces of methane, ammonia, and water vapor. But mostly the 2 lightest elements in the universe, hydrogen and helium, respectively. It has a troposphere, a haze layer, and a stratosphere, but mainly all gaseous or icy type layers, not solid land. Oops. Here's a closer look at the atmosphere. Here's a theoretical model for the interior of Jupiter, composed mainly of hydrogen in different forms. You have a mantle of molecular hydrogen, and as you get under higher pressures and higher temperatures, you have a outer core that is composed of metallic hydrogen. Hydrogen being a metal in its solid form, and hence with this metallic metal going around, Jupiter has a very large magnetic field, composed mostly of hydrogen and helium. Temperature and pressure in Jupiter increase with depth, At 20,000 kilometers below the cloud tops, high pressure forms liquid metallic hydrogen. This liquid hydrogen is the major contributor to the very large magnetic field, as we said. Has an iron-rich rocky core with a mass 10 times that of Earth, and maybe on the order of a little bit larger than Earth. So somewhere way down in the center of Jupiter is a rocky type core, like a big Earth. Jupiter emits twice as much energy as it gets from the Sun. This is believed to be gravitational energy leaking through the heavy atmosphere, but there's no real great explanation for this energy. If Jupiter had 20 times more mass, most of its mass being hydrogen, it would actually have been a star, and hence our solar system would have been a double star system. There are many double star systems out there. In fact, maybe as many as 50% or more of the stars that you see are double star systems. So Jupiter could have been a star. Maybe not. Not a chance. Jupiter has a significant magnetic field and is probably a very good example of the dynamo effect, where you have a spinning equator of metallic material, and in this case that spinning metallic material produces a magnetic field that's perpendicular to the plane of that spin. Hence it's aligned near the rotation axis itself. In the case of Jupiter, it's only 10 degrees off. For Earth, it's 11 degrees off. So this is due to the spinning of this metallic hydrogen core. As a result of this magnetic field, Jupiter exhibits auroras just like the Earth does. Jupiter's displays are much more energetic than the Earth's displays. It also has larger versions of the Van Allen belts. Jupiter's magnetic field is 20,000 times more powerful than the Earth's and 1,000,000 times more voluminous. If we look at Jupiter's magnetic field and its extension due to the solar wind pushing it out, it actually extends beyond the orbit of Saturn. And in fact, when Pioneer 10 ventured off beyond the orbit of Saturn, it still was able to pick up a remnant of Jupiter's field even at that orbit 5 astronomical units away from Jupiter. As we mentioned before in our discussion of comets, Jupiter was impacted by Comet Shoemaker-Levy in the early 1990s, and that comet broke up into 24 separate pieces, each of them impacting with more than atomic force, more than hydrogen bomb force on the planet, with massive explosions and energy on the planet of Jupiter. Jupiter is a valuable asset to the solar system as far as Earth is concerned because it probably eats up a lot of these comets and Earth-crossing type stellar probes and eats them up before they possibly could harm the Earth. So it's kind of like a big brother out there looking out for us. In 1994, series of explosions, each about 1 billion nuclear bombs. And one of these impact sites larger than the Earth itself. That concludes our relatively short lecture on Jupiter, the first of 3 lectures in this chapter.